All right, ladies and gentlemen, welcome back to another video with Mr. Kenton for AP Chemistry. And we're going to be continuing our discussion through intermolecular forces by talking about the properties of solids and then looking at solids, liquids, and gases more in depth. And as you notice here with this particular section, it's going to cover the rest of chapter 11, and it's going to cover the first section in chapter 10. And so just kind of as a heads up for you guys to mentally prepare yourselves, I'm going to be splitting up this particular section of the material into two videos because I don't want to overwhelm you with one really, really long video. So I'm doing this for your benefit. Just know that. All right. So if you guys are ready, I'm excited about sharing this, what we're going to talk about today, looking at the different properties of, specifically right now, we're going to look at liquids and energy changes. Okay. So let's dive right in. So, as we saw in the previous video, we introduced the idea of intermolecular forces, these interactions that occur between the molecules that make up our substance, right? And we noticed how in liquids and solids, the intermolecular forces could be a way to look at them and look at their strength was looking at melting and boiling points. Well, when we start to think about phases of matter, you guys probably already know you've got solids, liquids, and gases. And here are some things just to kind of put us all in the same frame of reference, right? I'm not going to read everything on this list because I trust that you guys can read. But you've got these different properties that correspond to gases, liquids, and solids. And so specifically, when we start to think about gases, they assume the shape and volume of their container. For liquids, they assume the shape of their container, but they only occupy a specific volume within their container. And then solids, they retain their own shape and volume within whatever container that they're situated in, right? And obviously, everything that's listed here on this table, it's not expansive, it's not exhaustive, it doesn't tell us everything, but it does give us some ideas of some things that we need to consider as we're moving forward. So just make sure that you're familiar with each of these characteristics that are listed here in this table. Now, as we begin to look at those, like I said, we're going to start by looking at liquids, then we're going to look at solids, and then we're going to shift into gases. That's where we're moving as we go through this video. Now, let's start by looking at properties of liquids. Now, liquids are going to vary in viscosity. And so if you think about that word viscosity, viscosity essentially is a measure of the resistance of a liquid to flow, right? And you've interacted with different liquids. Water, for example, is going to have something with a relatively low viscosity. But if you look at something like syrup, right? Syrup has a much higher viscosity, a much greater resistance to flow. Or if you even talk about oil, for example, and oil is going to be very different, like motor oil, when I say oil, not cooking oil. Now, the thicker the liquid is, now notice that thicker is in quotations here, right? When we start talking about the liquid itself, it is a liquid that has more viscosity, has a greater resistance to flow within our container, within whatever it is that you're measuring this ability to flow in. Now, what we do find is that the stronger the intermolecular forces are within that substance, what we tend to find is that there's a higher viscosity. Now, again, just looking at a series of hydrocarbons here, when you're looking at these hydrocarbons, they all share London dispersion forces because they're all non-polar. When you go from hexane to heptane to octane to nonane to decane, we see that the viscosity is increasing. So decane has a greater viscosity. It's going to resist flowing in comparison to hexane. Now, please keep in mind, you're not going to have to calculate the viscosity of any substance. So don't worry about these specific numbers, but they're just there to give you that as context. So viscosity is an important property of liquid to consider its resistance to flow. Now, we also note that if we increase the temperature on a liquid, the viscosity of that liquid tends to decrease, because what you're doing is you're causing the molecules to spread further apart. They're interacting with each other less, and so it makes it easier for them to move over each other. Now, another property of liquids that you should also consider would be surface tension. Now, surface tension can be referred to as a thin skin that's on the surface of your liquid that's in question that we're dealing with. And we want to think of surface tension, how it functions. The molecules that make up the liquid, when they're inside the liquid, like if you look at the container that's listed here, the molecules are equally attracted to the neighboring molecules that are in the substance. Now, unfortunately, the surface molecules, they have less interactions that they can form because they're not as surrounded by as many particles. So surface molecules are only attracted inwards towards those bulk molecules. So what's going to happen is that those surface molecules are going to be packed in much more tightly at the surface than the bulk molecules that are distributed throughout the rest of the substance. And so if you even notice the surface here, they're much closer together, whereas below the surface, the molecules are a little bit more spread apart. And so these molecules up at the top can form and make surface tension, which can serve as that thin skin on our liquid. Now, by definition, surface tension is the amount of energy that's required to increase the surface area of a liquid. Now, it sounds kind of like a weird definition, but just kind of roll with it. And so what we see is that the stronger the intermolecular forces are within our liquid, then the greater the surface tension is for that particular substance, for that particular liquid. And if you think about it, that's why certain insects like water striders, they're taking advantage of the surface tension of water, and that's what allows them to be able to move across the surface without sinking into the water. All right, now we're going to kind of take a shift here from looking at specifically liquids, and we're going to start taking a look at phase changes and energy and how those are related within these different processes. And so from this particular diagram, I want you to notice that on the y-axis, it's just measuring the energy of the system. So as we move up, it's telling us something about the energy of that overall substance. And so what you can see here is that when we compare solids, liquids, and gases, our solids have the least amount of energy, our liquids are in the middle, and then our gases are going to be the substances that have the greatest amount of energy within their particular particles. Now, you also are going to notice that we've listed all the different types of phase changes that can occur. And I want to focus first on the phase changes that are in red. And so when you look at this graphic, I want you to notice how all of those arrows are moving up, right? So going from solid to liquid, liquid to gas, and then even from solid to gas. Notice that all of those show an increase in the energy of the system. So what that's telling us is that energy has to go into the solid to convert it to a liquid, or energy has to go into the liquid to convert it to a gas, or energy has to go into the solid to convert it directly to a gas. So each of those processes that I just mentioned that are highlighted here, melting, vaporization, and sublimation, each of those processes would be considered endothermic because energy is going into the system, which is our substance, the solid, the liquid, or the gas. Now, the substances that are listed, or these phase changes that are listed in kind of this greenish color, going from the gas to the liquid, liquid to the solid, and gas to the solid, notice that those arrows are moving down, right? And so that means that energy is leaving the system. There's an energy that's being released. So each of those phase changes going, so condensation, freezing, and deposition, those phase changes would be exothermic. They are releasing energy into the surroundings. So the endothermic phase changes, the phase changes that require energy would be melting, evaporating, boiling, and sublimation. The phase changes that are exothermic, the phase changes that are releasing energy, are going to be freezing, condensation, and deposition. All right, hope that makes sense. Now, more on phase changes in energy. So for each substance, they're going to have their own unique heat of vaporization and heat of fusion. Now, heat of vaporization is the heat energy required to vaporize, that should say vaporize, guys, a given mass of liquid at a constant temperature. All right. So essentially, this is the energy that's required to take the mass of a liquid to take it into the gas phase. Heat of fusion is the energy required to melt a given mass of a solid at a specific temperature. Okay. So most cases, heat of fusion is going to be looking at the energy required to convert the solid completely into a liquid. Now, this also brings me to what's called a heating curve. You could also look at something called a cooling curve as well. So a cooling curve would just be the exact opposite. It's going from a high temperature going to a low temperature. Now, within the diagram, I want you to notice some very important things within this heating curve. Notice that it's broken up into sections. I guess even before that, pay attention to the axes, right? So on the y-axis of this graph, we've got temperature in degrees Celsius. And on the x-axis, tell us that we've got heat that's being added into our substance. In this case, we're dealing with water. Okay, and so then what I want you to notice, guys, are the different sections that this is being broken off into. So you've got section AB, which corresponds to solid ice. You've got section BC, which is where the melting is occurring. That's where you've got ice and liquid water present at the same time. You've got segment CD, where you have only liquid water. You've got segment DE, which is going to be the vaporization of the water. So that's where you're going to have liquid water and water vapor. And you've got section EF, which is going to be when you have just gaseous water. Now, something that I want you to pay attention to is what's going on with the temperature at each of those sections. Now, if you're looking at sections A, B, C, D, and EF, you should notice that as heat is being added, it's causing the temperature of our substance to also change. Right? So from A to B, from C to D, and from E to F, as heat is being added, there is a temperature change. And so what that means is that the kinetic energy of the particle, the average kinetic energy of the particles, is increasing. Now, notice that at segments BC and DE, aka the phase changes, notice that as heat is being added, the temperature is not changing. So from segment BC, the temperature remains constant until all of the ice is converted to a liquid, and then the temperature increases. Same thing at DE. All of the water is being heated, and so as it's going from D to E, the temperature is staying constant until all of the water is converted to a gas, and then the temperature begins to increase. Okay, at segments BC and DE, this is where we're going to have a change in the potential energy. And at both of those segments, what's taking place are the intermolecular forces of attraction between our molecules are being weakened or they're being broken altogether. That's what's taking place at BC and DE specifically. So A, B, C, D, and EF, we're getting a change in the average kinetic energy, or a change in kinetic energy. But at BC and DE, we're getting a change specifically in potential energy. And so for reference, BC would represent the heat of fusion, or that area of heat of fusion, and then DE would be looking at the heat of vaporization for water in this case. Now, I went ahead and said these things, so notice temperature, average kinetic energy during a phase change, such as boiling, does not change. And so any heat that's being added during boiling gives molecules enough energy to escape the liquid. So we're breaking intermolecular forces, just to kind of recap. Now, if you noticed, the segment for the vaporization line was much longer than the melting line. And so generally it will take more heat to vaporize a liquid than to melt a solid. So delta H of vaporization, as it's abbreviated as, is typically greater than delta H of fusion, so the enthalpy of fusion. And so you might be wondering, well, why is that the case, Mr. Kenton? Why is it like that? Well, when you start to think about it, what's taking place is that when something is vaporizing, when it's going from a liquid to a gas, every intermolecular force is being broken because now the particles are separating and they're no longer interacting with each other as often. But in the context of a solid, they're more tightly packed together. All we're doing is we're adding energy so that the solid can kind of spread out a little bit. So only some of the intermolecular forces are being broken during melting, which is why the enthalpy of vaporization is greater than the enthalpy of fusion. And this chart just kind of shows you that comparison. And again, it doesn't matter where we're looking at something that's polar or nonpolar, covalent or metallic, or it doesn't matter. You can notice that the purple graph is showing the heats of fusion, and the blue portions are the heat of vaporization. So for butane, it takes 5 kilojoules per mole to melt it, and 24 kilojoules per mole to vaporize it. For water, 6 kilojoules per mole to melt it, 41 kilojoules per mole to vaporize it. And again, it's accounting for the fact that all the intermolecular forces are being broken in vaporization, whereas only some are being broken in fusion. All right, let's talk about liquefying gases. So if you have a gas, it can be liquefied by increasing the pressure at a given temperature. And so if you think about it, pressure is a force that's being applied to a substance. If you start adding pressure to a gas, you're going to cause the particles to move closer together, and eventually they're going to form intermolecular forces and go back to the liquid phase. Now, the critical temperature of a substance is the highest temperature at which a substance can remain a liquid, regardless of the pressure that's being applied to it. Okay? And so once it gets to that temperature, once you get there, it can stay a liquid, but if you go over it, then it has to go into the gas phase because there's too much kinetic energy. The interactions are not going to be able to be formed, and they're just going to stay in the gas phase. There's also something known as the critical pressure. And so the critical pressure is directly related to the critical temperature. This is the pressure that is going to cause the liquid to remain a liquid at that given temperature and pressure. Now, when you look at various substances, like you look at this table, it's listing the critical temperatures and pressures of various substances. And so you've got things like ammonia, 405.6 for its critical temperature. Its critical pressure is 111.5 atmospheres. Phosphine, 324.4, 64.5. Look at something like water, 647.6 is its critical temperature, and 217.7 atmospheres is its pressure. Then you got hydrogen sulfide, 373.5 and 88.9. Now, something that I want you to note, I went through those very specifically, as the intermolecular forces of attraction increase within those substances, so you think about ammonia and water, for example, they both contain hydrogen bonding. And so when you compare those to phosphine and hydrogen sulfide, for example, phosphine only has dipole-dipole interactions, same with hydrogen sulfide. Notice that those critical temperatures and pressures are much lower for those substances. So stronger intermolecular forces tend to lead to higher critical temperatures and critical pressures that our molecules can attain before they can be converted into a gas. Or if you're going from a gas back to a liquid, if that makes any sense. Now let's take a look at vapor pressure and boiling liquids. Now, when you think back, we had our surface tension, we're looking at the surface of a liquid. The reality is that some of the molecules on the surface of a liquid are going to have enough energy to escape the attraction of the liquid. And so when that happens, those molecules go ahead and exit the liquid phase and move into the gas phase. You can think of this is like evaporation, right? If you leave a water bottle open, what happens is it's not the molecules at the bottom of the water that are escaping, it's the ones that are on the surface. And so over time, as more and more particles have energy, they escape out and they move into the gas phase. Now, when we start talking about those particles that are escaping into the gas phase, as the number of molecules in the gas phase increases, assuming we're in a sealed container, some of the gas phase molecules will strike the surface and they'll return to the liquid phase, right? So you've got liquid particles that are there, you've got gas particles that are in your container. Those gas particles are going to strike the surface of the liquid and they're going to return back into the liquid phase. And so it's going to be back and forth, right? It's an ongoing process, and it's going to continue until an equilibrium is reached, until the number of particles that are escaping and the number of particles that are going back in are the same. Excuse me, the rate at which that's happening is going to be the same. And so after some time, the pressure of the gas will be constant, and that's what's going to be known as the vapor pressure, right? So once that pressure of the gas no longer changes anymore, once that pressure is constant, that means that you've got the vapor pressure of that particular gas. And if you look at this apparatus here, it's called a manometer, and it's like a manometer in a sense. And so what it's doing is you've got your liquid that's in the container, and you got the gas particles that are escaping. And so once the equilibrium is achieved, what's going to happen is it's going to move. We're assuming that it's attached to a container that has mercury. So what it's doing is it's displacing the mercury and shifting it over to the right. And so once that shifting stops, that's when the vapor pressure, or the vapor pressure of the gas, has been achieved, right? When that gas is no longer exerting a force that's causing that liquid to shift over any longer. Now, let's talk about this equilibrium that I just mentioned. So dynamic equilibrium is the point within our liquid where as many gas molecules escape the surface as are striking the surface. And so the vapor pressure is the pressure exerted when the liquid and vapor are in dynamic equilibrium, right? So when the gas molecules that are escaping the surface and the gas molecules that are going back into the surface are constant. All right, keep taking a look at vapor pressure and boiling of liquids here. So when we talk about boiling, if you've ever had the pleasure of doing any cooking, like cooking pasta, for example, water is going to boil when the external pressure that the water is in is equal to the vapor pressure of the liquid. And so what we see is that the temperature of the boiling point increases as we increase the pressure on our liquid. Now, when you look at each of these particular substances that are listed here on this graph, you've got the vapor pressure in torr, and you've got the temperature on the x. So temperature's on the x-axis, vapor pressure in torr is on the y-axis. And so you've got various different liquids that have been listed here. Now, on this diagram, you notice there's a solid line that's going horizontally across at 760 torr. That's the normal boiling point for a substance. And the normal boiling point always occurs at a pressure of either 760 torr, 760 millimeters of mercury, or 1 atmosphere. So it's not dependent upon temperature. And so we look at, for example, diethyl ether has a normal boiling point of 34.6 degrees Celsius. Ethyl alcohol has a boiling point of 78.3 degrees Celsius. Water has a boiling point, a normal boiling point of 100 degrees Celsius. So this is all assuming that we're at 1 atmosphere pressure, 760 torr. Now, when you look at these substances, right, you notice that the vapor pressures at given temperatures are very different. So you look at diethyl ether at 0 degrees Celsius, it has a vapor pressure of 200 torr approximately. Whereas you look at ethyl alcohol and water, they're both right a little, pretty much close to 0, right? Like ethyl alcohol is a little bit higher. As we move to 20 degrees Celsius, we see that water's got a vapor pressure of, all right, maybe 5. You've got ethyl alcohol, maybe that's at 10 to 20. And then you've got diethyl ether, it's at like maybe 450. And you just see that, right? And so a substance with a high vapor pressure is said to be volatile. So like diethyl ether at a given temperature has a significantly higher vapor pressure than ethyl alcohol or water. And so because of that high vapor pressure, we would say that diethyl ether is a volatile substance. And all that means is that it's going to readily evaporate. So it's easier for its surface particles to escape into the gas phase. Now, that volatility is also going to tell us something about the intermolecular forces. So diethyl ether, we would say, has significantly weaker intermolecular forces than water. Water has hydrogen bonding, right? So I hope that makes sense. Now, again, continuing with this vapor pressure and boiling of liquids, there are multiple ways that you can get a liquid to boil. The first is to increase the temperature of the liquid, right? So you look at our heating cooling curve we looked at, you increase the temperature, you get the particles moving fast enough, they're going to convert into the liquid phase because they're going to attain too much kinetic energy. We're going to break the intermolecular forces of attraction, and it goes to the gas phase. The second thing you can do is you can decrease the pressure. So essentially what you're doing is you're increasing the space at which the particles can interact, and so then they begin to separate. So using something like a vacuum pump. Now, you think about this, a very practical way in which this plays itself out, pressure cookers, right? So pressure cookers operate at higher pressures. That's kind of what they do. Shocking, it's in the name. Now, at high pressure, what happens is the boiling point of water is higher than it is at 1 atm. So at 1 atmosphere, we know that water's boiling point is 100 degrees Celsius. Well, if the pressure is higher, the temperature that it boils at is much higher. Now, as a result, if you're in a pressure cooker, what's going to happen? It's going to allow the water to get to a higher temperature, and ultimately, the temperature at which the food is being cooked is higher, and so then it reduces the cooking time on whatever it is that you're trying to cook. See, you guys didn't know that cooking actually took advantage of properties that you learn about in chemistry. You're not going to look at cooking the same way ever again now. Maybe you won't, I don't know. All right, now looking at the boiling points, like what we saw on the previous slide with those vapor pressure curves, that the boiling points increase with molecular weight, as long as the intermolecular forces are similar. That's not necessarily true on the previous slide because we had different intermolecular forces that were at play. But what we do see is that overall, the boiling point of a substance is going to increase as the molecular weight goes up, as long as you're comparing similar intermolecular forces. So London dispersion forces with London dispersion forces, dipole-dipole interactions with other substances with dipole-dipole interactions, so on and so forth. So for example, when you look at methane, ethane, and propane, ethane has a much lower boiling point than ethane, which has a much lower boiling point than propane. And again, we're seeing it from that weight perspective. And it has to do with the intermolecular forces, right? The intermolecular forces in C3H8 are stronger. The LDS forces in C3H8 are stronger in CH4, so we get that increase in the boiling point. That makes sense. All right. And I believe, ladies and gentlemen, that's our last slide for the day. Hope this makes sense. Hopefully that was insightful. We're going to pause here, and in the next video that's going to come out, we're going to be looking at solids and gases and looking at phase diagrams. So I hope you're able to come back and watch with me. Hope this was helpful. Let me know if you have any questions, or let Mr. Lambert know if you have any questions. And, we'll see you guys again real soon. Take care.